All right, so this video is going to go over your unit review for your wave packet. Okay, so we're going to go. This is some good practice, but I'm noticing on this review there probably could have been a little bit more that we need to improve on, and there's some things that I'm going to mention that will definitely not be on the test. So I'll talk about that here in a second. But if your goal is to look at this wave review video and you think this is it, this is all I need to know, okay, I would probably go back and look through the packet a little bit more thoroughly. I would definitely go back and look at your old quiz and stuff and see what was asked there. And then I would look at the stuff that was asked after the quiz, like when we started doing standing wave stuff, like where you had to draw so many nodes and antinodes, things like that. Going over constructive and destructive interference, more of that terminology stuff. So this is a good practice for your review, but by all means, please go back and look through your packet. Make sure you're paying attention to any terms, okay, anything that you may think that I might not know what that word means, I would study that, okay? So there's a lot more conceptual and vocabulary on this test than mathematical, okay? There is some math, but that's not gonna be the bulk of it. And we'll do a little bit of math on here, but if I was gonna go back and look at any math stuff, I would go back and look at the standing wave homework. Okay, so when we had to draw so many loops and then figure out what was the wavelength and then we could find velocity, or I would go back and look at one of the previous homeworks before the quiz where we did the whole C equals frequency times wavelength, or V equals frequency times wavelength, or V equals wavelength divided by T. Okay, so that basic math stuff, so make sure you go back and look at that. All right, so let's get started. So one, explain the difference between a longitudinal wave and a transverse wave. Okay, so first of all, a transverse wave looks like this. Okay, so that's what a transverse wave looks like. And if you had a particle that was sitting there floating on it, okay, like right there, what's going to happen is that particle is going to bob up and down while the wave is going to continue to go to the side. Okay, so a transverse wave is basically when particle movement is perpendicular to the wave direction. Okay, so my wave direction is horizontal in this case. It's moving to the right. And my particle movement is vertical. It's bobbing up and down. Okay, so that's what makes a transverse wave. Okay, versus a longitudinal wave. A longitudinal wave is going to look like this. It looks kind of like a slinky, is where you have it compresses and then it starts to stretch back out and then it starts to come back in and it starts to compress again. So that would be a longitudinal wave. So if you had a particle on there, okay, what happened is that particle is going to go vibrate side to side, and your wave is also going to move horizontally as well. Okay, so a longitudinal wave or a compressional wave, both are the same thing. That is where particle movement is parallel to wave direction. Now, give an example of a longitudinal wave. So a longitudinal wave is going to be something like sound. So sound is one where those particles are going to vibrate back and forth. Okay, and so make sure you can label longitudinal wave. So if I had a longitudinal wave that looks like this, so it's stretched out and then it starts compressing here, I would make sure I would know that this would be a compression. And the stretched out part, remember that was called a rarefaction. Okay, so make sure you get that part right. Now, give an example of a transverse wave. Transverse wave is going to be any of the electromagnetic ones, where it's going to be things like radio wave, microwave, infrared, visible light, UV, X-ray, and gamma. Okay, those are all electromagnetic waves. Okay, so any of those are going to be a transverse wave. And we'll go over labeling a transverse wave here in a second. What's the difference between a mechanical wave and electromagnetic? Okay, so electromagnetic, okay, does not need a material, so no material medium. Okay, it can go through space or a vacuum just fine. It doesn't need air, it doesn't need water, it doesn't need a rope, anything like that. Versus mechanical, it needs a material medium. It has to have something physical, like air particles, water molecules, like a rope. Okay, so it needs a material medium. So remember, your electromagnetics are these right here. Basically, anything that's not that is going to be considered mechanical. How does an air particle move as sound travels by? Okay, so basically what happens is you have an air particle that's going to vibrate. Okay, so it's going to vibrate side to side. And you have another particle here that's going to come in contact with the energy, and that begins to vibrate. And then that particle next to it begins to vibrate. Okay, so that's basically what happens is the particle vibrates back and forth, transferring energy to the particle next to it. Okay, so that's why it looks like a longitudinal wave. Now, what type of wave can travel in space? We just talked about that. That is electromagnetic. And what type of wave cannot? That is a mechanical. Okay, so that is one of the reasons why you cannot hear sound in space. Sound needs air molecules to transfer energy to. In space, there is none, so there's nothing you can hear there. Label wavelength and amplitude in the graph below. So we're going to look at the graph here. So if I were to label this wave, okay, the top of the wave is called a crest. The bottom of the wave is called a trough. Okay, you have an origin line right here. Okay, that is basically the middle point. Okay, and then basically the height from the origin line to the crest or the trough, it does not matter which one. Okay, both are the same. That would be considered amplitude. And just make sure you know what a full wavelength is. Okay, its full length has to be one full crest, one full trough. So like here to here, this would be a wavelength because you started a crest and you ended a crest. Okay, so that would be one. Or if you started here, like if I'm gonna use a different color. Okay, so let's say I started here, one full crest, and then one full trough. That would be a wavelength there. Okay, so this graph, this is what I was talking about here is, as long as you're good at labeling stuff and you know that how like amplitude is the height of a wave and what a full wavelength is, you're gonna be pretty good there. Okay, what happened here was this time is technically also a distance. So this is a light year. A light year is actually a distance. It's basically how far light travels within a year. Okay, so what we're gonna do is don't worry about. I'm gonna show you how to do this, but don't worry about trying to do light year stuff. We're not gonna try to do that on the test. Okay, so calculate the wavelength, amplitude, and frequency above. So I'm gonna figure out how long is one full wave. So if I start at 0, let me get a different color. I'm gonna go to green. Okay, if I start at 0, my wave starts here. I go down. That's half a crest, one full trough, and then another half of a crest. So it goes from 0 to 50. Okay, so if that was meters, you would just say 50 meters. Okay, in this case, we're just gonna say 50 light years, and we're just gonna be done with that part. Okay, amplitude, we're gonna figure out how high is the wave. So it goes from 0 to 90. Just be careful with this. That is a millimeter. Okay, so there are 1,000 millimeters equals 1 meter. Okay, so I'm gonna take that 90. Okay, so my amplitude is gonna be 90 divided by 1,000. And that's going to give me 0.09 meters. So that is the height of my wave. Now frequency is 1 over t. So that is 1 over the time it takes for one wave. It has to be in seconds though. So on my key, you're going to see some numbers there. So t would be, well, how many seconds are in 50 years? This is why I'm not going to do this on the test. This is a lot. Okay, so there are 50 years. You're going to multiply that by 365 days in a year. There's 24 hours in a day. There's 60 minutes in an hour. And there's 60 seconds in a minute. And that means there is 1.57 times 10 to the 9 seconds in 50 years. Okay, so now you have your value. So 1 over 1.57 times 10 to the 9th. And you get a frequency of 6.37 times 10 to the negative 10 hertz. Okay, so don't get too hung up. Mostly what we do is we just give you the time and you just do F equals 1 over T. And be done with it. You wouldn't have to convert 50 years to seconds, so don't freak out about that. We're not going to do that. Number 9, what wave property determines the pitch that we hear? So what determines pitch is going to be your frequency, how many waves are happening, okay, in that time. All electromagnetic waves have the same speed, okay? So radio all the way through gamma all travel at the speed of light. C equals 3.0 times 10 to the 8th. Okay, so we will give you that value. You don't need to memorize it. 11, a wave has a period of 8 seconds. What is the frequency? So again, it would be look more like this, more basic stuff. F equals 1 over T, so 1 over 8. And that gives you 0.125 hertz. Now, a radio wave has a wavelength of 50 meters. What's its frequency? So you got to make sure when you're doing those math problems, make sure you know that you are dealing with an electromagnetic wave. If you weren't, we would have to give you the velocity of that material. Okay, so if we mention sound or something like that, on your formula sheet, you'll see V equals 340 meters per second. So if I ask for anything to solve with sound, you would use this. Okay, that would be your velocity, and then you would just plug in V equals frequency times wavelength or whatever you need there. Okay, if you're not dealing with sound, or if you're dealing with electromagnetic, you're going to do this equation right here, C equals frequency times wavelength. C is the speed of light because that is what all EMR waves travel at. Frequency we don't know, that's what we're looking for, and your wavelength is 50 meters. So divide both sides by 50, and you get a frequency of 6 million hertz. Okay, 13. Okay, what is the amplitude and wavelength of wave A? So wave A is right here, so wavelength. So we're going to start right here. We're going to go up. That's one full crest, one full trough. So for A, my wavelength would be 2 meters. Okay, and what is the amplitude? Okay, so let's see, how high did A go? Okay, my amplitude would be 0.50 meters. Let's go ahead and do B while we're at it. Okay, so B, I'm going to use a different color. Starts here, we have one full crest, one full trough. Okay, so your wavelength is going to be 4 meters now, so 4.0 meters. Okay, your amplitude, looks like it only got up to 0.25, so 0.25 meters there. Now 14, if wave B has a frequency of 50 hertz, what's its speed? Okay, so V equals frequency times wavelength. Okay, so V equals, my frequency is 50. Okay, what was my wavelength for B? My wavelength was 4 meters, so 50 times 4, and that gives you 200 meters per second. 15, don't worry about this problem. Okay, this goes back to, we did this a long time ago with circular motion. Okay, if you want to find frequency and you have how many waves or circles there were in a certain amount of time, okay, frequency equals cycles over time. Okay, so you would just do 8 cycles over 50 seconds. And that'll give you a frequency of 0.16 hertz. Okay, so again, don't get too hung up on that one. So for math calculation stuff, one thing I would make sure I go back and look at in your homework is, what if I gave you something like this radio station had a frequency of 92.5 megahertz. Okay, so pay attention to that prefix. We will give you that metric scale. Okay, mega is times 10 to the 6, so it means you have to change it to 92.5 times 10 to the 6. So just go back. Watch out for that. Okay, so make sure you use that. We're going to give you that chart, so it's there for a reason. Let's see, last bit is, this is good practice as far as terminology goes. Number 1, the combination of 2 or more waves that result in a single wave. So when I combine 2 waves, something's got to happen. The wave's either going to get bigger, okay, or it's going to get smaller. Okay, so regardless, it is some type of interference. Anytime you mix 2 waves, there's going to be some type of interference, so your answer would be I. Okay, so that is just interference. When you combine 2 or more waves, just basically to create a single wave. Now, it could be constructive, it could be destructive, but it doesn't mention which. It just means when 2 or more meet to make one single wave. 2, the change in direction of a wave when it encounters an obstacle or edge. Okay, so this is what we talked about is when I was talking in my classroom and how somebody can hear me down the hall. Okay, is because of that diffraction. Okay, it squeezes through that obstacle or that corner of the building, or the doorway, and then it spreads out around that corner and goes down the hall. Okay, so this is going to be diffraction A. 3, interference that decreases amplitude. Okay, so something that decreases is destructive. Okay, so that is going to be F, destructive interference. A pattern of vibration that resembles a stationary wave. Okay, so that is a standing wave. So remember, your standing waves looked like this, where you have a wave going this way, and then you have another wave coming back the same way with the same amplitude and the same frequency. Okay, and what's going to happen is it's not going to really look like the wave is moving at all. What's going to happen is it's just going to look like it's flip-flopping between a crest and a trough. So it actually doesn't look like it's moving side to side. It just looks like it's stationary, so that's why it's called a standing wave. It looks like it's standing in place. And the crest is just switching back and forth to a trough, and the trough goes back to a crest. Okay, so a stationary wave would be your standing wave. So the answer here would be C. 5, points in a standing wave that have no vibration due to destructive interference. So that means that no vibration means you have 0 amplitude. Okay, so destructive interference causes nodes. Okay, so remember, if you have no amplitude, that's a node. If you do have amplitude, like if it's constructive interference, that would be an antinode. Okay, so remember, a node would be like right here. So that's 1, 2, 3, 4 nodes, and your antinodes would be your maximums. So that'd be 3 antinodes. So 4 nodes and 3 antinodes. Number 6, the bouncing back of a wave when it meets the surface. That is reflection. Reflection is pretty simple. That's just when it bounces off something. Okay, so your answer is going to be D. 7, interference that increases amplitude. So it makes it bigger. Okay, so that'd be constructive interference. Okay, 8, sounds produced by interference of sound waves that are used to tune piano strings. Okay, so we didn't really go over this, but this would actually be beats, so I'm not going to ask that on the test. Number 9, the bending of waves as they pass from one medium to the other. Okay, so that'd be going like from air to water or water to air. That is refraction. That is B. Number 10, method of adding crests and troughs of interfering waves together to describe a new wave. Okay, that is the principle of superposition. All that means is when you just add up the crests and troughs and see what is your new amplitude going to be once those waves meet. Okay, so your answer is going to be G there. Okay, so just make sure that ends this one. Just make sure this is good practice, but please go back and look through like your old quiz, your old homeworks, and through your packet. Okay, because most of it was covered in here, but there are some pieces that were kind of missing there, so kind of go back through there and look through it all.